Hi, my name is David Heath, and in this brief video, I will be giving an overview of our paper, Zero Knowledge for Everything and Everyone, Fast ZK Processor with Cached ORAM for NCC Programs. This paper is joint work done by myself, by Yibin Yang, David DeBessary, and by my advisor, Vlad Kolesnikov. The four of us work at Georgia Tech in Atlanta, Georgia. I'd like to begin by starting out with a motivating problem. Consider the following scenario. Let's suppose that there is a hospital that has a certified database containing lots of sensitive patient data. At the same time, there's a researcher who has a patient study that he would like to conduct on the database. Both parties would like for this patient study to actually happen. There's a serious value that might come from this patient study. But at the same time, the hospital might be unwilling to give patient data directly to the researcher. After all, the patient data is sensitive, and in fact, the hospital might have its hand tied by legislation which prevents it providing data directly to the researcher. Now, one thing we could imagine doing is have the hospital perform the study on behalf of the researcher. But this is potentially problematic because the researcher might not trust that the hospital will conduct the survey correctly. That is, the researcher wants to get the result of the study, and they want some sort of assurance that the result of the study has something to do with the actual patient database that the hospital owns. There is a cryptographic technology called zero-knowledge proofs, which can be potentially used to help solve this motivating problem. In zero knowledge, we consider two parties, the so-called verifier and the so-called prover. The prover would like to demonstrate some fact to the verifier without leaking some sort of extra knowledge to the verifier. More precisely, the two parties agree on some formal statement. You can think of this statement as a proposition that the prover would like to prove true to the verifier. The prover has some side information, which we refer to as the witness, which helps the prover to show that this statement is true. Zero knowledge then allows the prover and verifier to communicate by some sort of cryptographic protocol. At the end of the protocol, the verifier becomes convinced that the statement must be true. The crucial point is that beyond learning the statement is true, the verifier learns nothing at all. Zero-knowledge proofs give a potentially elegant solution to our original dilemma. In particular, we can now set the verifier to be our medical researcher and the prover to be our hospital. The statement that they will consider is some formalization of the medical study, and the witness is the prover's certified database. Now the two parties can use a zero-knowledge proof to show that the patient study results in some particular results. Crucially, at the end of this study, the verifier will be convinced that it must be the case that the results are bound to the database, but at the same time will not learn anything about the specific contents of the database other than whatever is implied by the study results. Unfortunately, in practice, such applications are not yet possible for end users to construct. The problem is that, as I said earlier, the statement must be formalized in some way. So far, the systems that cryptographers have developed essentially require an expert to formalize these statements. In this work, we address this problem. We allow zero-knowledge proofs to be expressed as regular ANSI programs. Even end users who don't know anything about cryptography can use a language that they already know, namely C, in order to write down zero-knowledge proofs. The system is also efficient enough, via a number of improvements that we make in our paper, that applications like this particular one are far more realistic than they were before. At a very high level, our approach to handling NCC programs as zero-knowledge proofs is as follows. We start from some source NCC program. Then we compile the NCC program down to a custom assembly language using a custom compiler. From here, we host this assembly language on a virtual machine. This virtual machine can be understood as a sort of processor. Our processor, however, is not a piece of hardware. Rather, it is a cryptographic protocol that runs between the two parties. Therefore, each instruction of the source assembly language runs inside zero knowledge. By running all of the instructions inside zero knowledge, we essentially hide the execution from the program verifier. Nevertheless, at the end of the execution, the verifier becomes convinced that the program execution is valid. Our work includes improvements to all parts of this design stack. The cross-cutting concern here is efficiency. Zero-knowledge proofs, as compared to clear-text computing on a hardware processor, is very expensive. Therefore, it's crucial that at each part of this stack, we keep as much performance as possible. Therefore, each part of this system is custom designed. For example, our zero-knowledge machine is built on top of a custom protocol, and the machine itself is hand-tuned to be as efficient as possible for the underlying protocol. Similarly, we did not take an assembly language off the shelf, but rather designed a custom one. This decision was motivated by efficiency. By choosing a custom assembly language, we can rule out instructions which would become too expensive for the zero-knowledge machine, and at the same time, we can include new instructions which happen to be extremely efficient on our very unique hardware. The result of this emphasis on efficiency is that our system can run off-the-shelf Linux programs inside zero-knowledge. I'll talk about performance more at the end of this talk, but our system can run it up to 10 kilohertz, and we were able to take standard programs like sed and gzip and run them inside zero-knowledge. Let's next take a look at how the two parties actually run a given program inside zero-knowledge. Both parties will run the zero-knowledge machine locally on their respective device. The zero-knowledge machine itself is built from a complex circuit. This circuit holds algebraic values which are shared in an authenticated way between the verifier and the prover. The parties propagate these shares through gates using a cryptographic primitive called oblivious transfer. Although the low-level actions of the two players differ from one another, I would like for you to think that the two parties essentially operate in lockstep. That is, each one of them looks at a particular wire at a particular time. By executing a very large circuit, which encodes an entire processor, the two parties can step through the program instruction by instruction and eventually reach the end of the program. I would like to emphasize that while this is happening, the verifier is completely oblivious to the values on any of the wires. His shares do not convey any information about any internal circuit values. Only the prover knows the values on the wires. Part of our contribution was to build very efficient circuits. We did this in a number of ways, perhaps most notably through a highly efficient RAM. We showed that by adding caching to a previous state-of-the-art zero-knowledge RAM, we were able to greatly improve performance. Representing a large main memory inside zero-knowledge is the single most expensive component of our system. Fortunately, our improved caching technique reduces the cost of RAM by around 8 times. Recall that our goal is to implement arbitrary ANSI programs. In order to implement ANSI, we have to provide a standard library. Therefore, I'd like to switch topics and talk a little bit about how it is that we go about achieving the C standard library inside zero-knowledge. So for example, what does it actually mean that the program is going to read a file inside a zero-knowledge protocol? Zero-knowledge protocols don't have any notion of files. Our answer, which we think is very natural, is that we cause the prover to perform corresponding actions on her local machine and then return the answer of that action back to the zero-knowledge protocol as part of her witness. So for example, when the zero-knowledge program indicates that a file should be read, the prover will read that file on her local machine and then feed the answer as part of her witness into the zero-knowledge protocol. To achieve the standard library and some other use cases, we implemented a feature that we call prover oracle calls. A prover oracle call is a type of assembly instruction that behaves quite differently from other instructions in our language. Recall that our system emulates a processor via a cryptographic protocol. In normal execution, it is instructive to think of the verifier and prover running this low-level machine in lockstep, instruction by instruction. In order to perform each instruction, the two parties will perform synchronized operations. The actual lowest level cryptographic details differ between the two parties, but at this level of abstraction, the parties essentially perform the same actions. So for example, to perform an add instruction, both parties will look up values from the processor registry, add the values together, and then store them back to the registry. Oracle calls are different. When an oracle call occurs, the verifier will do nothing. In essence, the verifier simply goes to sleep and waits for the next instruction. The prover, on the other hand, performs some meaningful actions. Specifically, the prover maintains what we refer to as the oracle table. This table holds a list of procedures which can be indexed by some identifier. When the oracle instruction occurs, the prover goes to the table, looks up the corresponding action, and then runs that action on her local device. The point is that by incorporating this simple mechanism, this single instruction, we have a way by which the prover can escape the zero-knowledge environment and perform actions that are needed to implement the standard library. Now that we've talked about prover oracle calls, I'd again like to shift directions and have a look at our instruction set. On the slide, I actually have our entire instruction set written out. We have instructions that handle algebra, control flow, memory operations, and special instructions for handling the prover's witness. As I mentioned earlier, this instruction set is specifically designed with zero knowledge in mind. For example, I'd like you to notice that conspicuously missing is any sort of algebraic operation that performs something like division. This is not limiting because we have access to prover oracle calls. For technical reasons, division inside the zero-knowledge protocol is quite expensive. However, we can use prover oracle calls to divide numbers quickly using a procedure. In particular, the procedure outsources division to the prover. This outsourcing is achieved by a prover oracle call. When the oracle call occurs, the prover locally divides the two numbers and feeds the result back into the machine. The answer that the prover feeds back into the machine can be quickly checked using the algebraic instructions that are provided in our instruction set. I'd like to use my last few minutes to discuss the efficiency of our system. The vast body of prior work on zero knowledge looks at circuits, not at general purpose programs. It is for this reason that I claimed earlier that current zero knowledge state-of-the-art requires an expert to craft proof statements. It is difficult to express complicated statements as circuits. There is some work that also takes a processor-based approach. However, these prior works are very, very slow in comparison to our work. These processors are able to run at about 1 Hertz or even less, and they can only support small main memories. Given that these approaches produce such weak machines, there is no hope to approach the level of generality that we take for standard C. In contrast, our system runs about 10,000 times faster and can support tens of megabytes of main memory. We get this performance by a number of novel zero-knowledge improvements that I mentioned earlier. Since our machine is powerful, we are able to support arbitrary ANSI programs. Of course, simply providing a powerful enough machine is not enough. We also had to make some design decisions, like the prover oracle calls that I described earlier. To give a little more sense of efficiency, I'd like to tell you about one of the benchmarks we ran on our system. In this benchmark, we show that we can use our system to allow the prover to demonstrate to the verifier that there exists a bug in a particular program. This bug is triggered by a specific malformed input. And at the end of the execution, the verifier becomes certain that there is a bug, but learns nothing about the program input. The particular benchmark I want to talk about is a bug that used to exist in the Linux program sed. Essentially, this bug would, on certain inputs, trigger an infinite loop that causes the program to override all of memory and eventually, on most systems, leads to a segmentation fault. This bug involves executing hundreds of thousands of instructions and consumes a large amount of memory. Nevertheless, our zero-knowledge system was able to prove the existence of the bug in around 36 seconds. We've now taken a very high-level look at our approach to handling zero-knowledge proofs expressed as ANSI programs. To recap, the way that we made this realistic was by designing a number of custom zero-knowledge components, like a custom protocol, custom process architecture and instruction set, and a custom compiler and standard library. The resulting system is powerful and efficient. It can run tens of thousands of times faster than prior work and can handle a large main memory. We believe that this work will help to enable powerful and interesting applications like the hospital use case I spoke about at the beginning of this talk.